Hi everybody. So we've just saw how we can use cosine as a way of calculating a t prime that lets us ease into our t change into a nonlinear function on our t. So we have this ease in, this slow acceleration feel. It ends up faster than before, and it gets there in the same time, but it starts slowly, so we feel like it's accelerating. So the problem was that it still had this sudden stop. So ease in and clunk at the end of the keyframe, and ease in and clunk again. Now we could ease in only in the first one and then maintain the speed throughout, and that would look a little better, but we're still having this funny change of direction and it stops without slowing down. So let's learn about a very similar function called, and you guessed it, ease out. So if we've learned ease in, let's now think about ease out. Now what I'm going to do is I'm going to skip a lot of what I've did above and just show you what it looks like and how it works. So again, here's what we want to do. T of 0 to 1, this is time. Then we have our linear function. Our ease out is the pink on the bottom. Ease in, I should say. And then ease out, it'll be like this. Okay? Yeah, I should probably fix that. Where it starts up really quickly, but then it decelerates, and eases out and goes very slow until it stops. So you get that nice, smooth finish feel. And the way we can calculate this is we use t prime is going to be the sine of t times pi over 2. And the reason that works is because of how awesome sinusoidal functions are. My sine function is like this. And then what's going to happen here is pi over 2 is right there, okay? Pi over 2 is right there. So I'm taking this region here, right? And then going, when t is 0, I get 0. When t is 1, I get pi over 2. So I'm taking this region here and mapping it to my t prime, which starts at 0 at the bottom and 1 at the top. So I'm actually going to get my desired pink line. Really nice. So let's just go look at the code. So we've seen the linear, we saw ease in, here's ease out, just like I showed you. Sine of t times pi over 2. So first of all, this is linear, bam, nothing, it's all kind of rigid, bam, bam. Remember, ease in, you hit the bottom, stop suddenly, ease in. Now let's hit one more time. Let's use ease out. So it starts full speed and it softly stops. Look at the soft landing. Look at that, how nice that is. It starts full speed, no ease in, just ease out. And it eases into that final spot. So it jumps out and then eases in. Okay, cool. So you're probably guessing, all right, ease in, ease out. How do we combine them? There's a couple of ways you can do it, but I'll show you one really simple way. So let's learn how to do ease in and out all in one go. So again, I'm going to draw this sinusoidal function, and I'm going to actually just continue it a bit, whatever. So this is our sine function. Now you probably are having trouble getting your head around all these pieces, so I'll draw it out for you. If I use my t 0 to 1 over time, here's my linear. What would ease in and ease out look like? Ease out is this one. Ease in is this one. Well, what we kind of want is ease in the bottom half here, and we want ease out for the top half. So we kind of want to go like this and up like an S. So it would be really nice if we could ease in for the first half and then ease out for the second half. Get an S curve. So if you look at our sinusoidal function, you can see, oh, there's a couple spots. I can go from here to here. This gives me my S I want. And we can do it all in positive if we wanted to, right? We could do this one here. So we could do like earlier and do like, minus and plus and then figure out the ratio. But someone's already figured out how to simplify it for us. And again, it uses cos. So I'm just going to show you what we do, and hopefully you can see how it works. So cosine goes like this, remember? From 1 to -1, this is 0. And to 1 again, this is pi 2 pi, okay? And so what we do here is we realize, just like before, that we have the shape we want right here. This is an S, but it's inverted, if we start from 0. And it's really nice to start from 0. So we can do the 1 minus to invert that again. So I'm going to spell out exactly how we do it, and then I'll go through how it works. So t1 equals 1 minus cosine. Now, 1 minus flips it this way, right? So I take my cosine and I flip it. That's great. But we have a couple of problems. I should probably move that a little bit out of the way. There we go. We have a couple of problems. I want this S curve. First thing I'm going to do, I 1 minus it, and I'm going to get the right shape. But previously, I was going from 0 to pi over 2. Now, I need to go from 0 to pi. So that's the first difference. Okay. So t times pi. I should probably have a pencil, Jim. Okay, so t times pi. When t is 0, it's 0. When t is 1, it's all the way to pi. Now, the other problem is it goes into negative territory, which really makes things strange. What do we do about that? Do we add 1? We could add 1 and bring it up, but then we minus 1, so it gets kind of weird. Okay, so we can look at this any number of ways. We could imagine, like I said, adding 1, bringing it up, and then 1 minus all of that. 1 minus minus 1 is plus 1. It gets kind of weird. But it turns out that all that we have to do is divide everything by 2. Now let me explain why that works. I'm going to draw this function out. So if I do 1 minus this s function, when t is at 0, I get 0. And when cos is at 0, I get 1 minus 0, so I get 1. So this will go, the first part of the s curve will go up to 1 like this. Okay. And then when it goes to negative, 1 minus a negative number is a plus. Okay. So at the bottom here, I have 1 minus minus 1. It goes up to 2. So this goes all the way up to 2, but t is supposed to stop at 1. Okay, so all that we do is we divide by 2. Now if we divide by 2, everything comes down to half. 0 to 1, and I get my nice S curve, which ends at 1. Okay, so this is the function we use, and that's how we derive it. So let's go back and let's look at our demo. Okay, so here's our demo. Ease in we did, ease out we did, and ease in out 1 minus cos t times pi all divided by 2. Okay, I'm going to run that. Okay, ease in, stops, eases in, it's quite nice. Ease out, right? Slows down when it hits the end, nice. So then just ease in and out. See? Eases, look how nice that looks. There's no rigid stop. It slows down to come in, slows down to come out. Cool. So it does that S-shaped curve that we want. So this is a really clever solution. Instead of modeling the acceleration and where we start deceleration and starting to think about it analytically, we can cheat. We know how long our length is. We use this idea of a parametric function to go from the beginning to end and interpolate the position. But then we modify the interpolation rate. We modify the t in a nonlinear fashion, and we get this really nice result here. Now there's one last example I want to show here. And it's called level in and out, and it's a little bit less clean than these other ones, but I'll explain it nonetheless. It's called leveled ease in out. You might have noticed from the example it's kind of dramatic. Whoa, like a lot of acceleration, a lot of deceleration. It feels a little bit active, high energy. Okay, and as an artist, or if you're creating a device or a game or some kind of animation, you might want to have it more subdued. So what we can do is we can make this more subtle. We can make the effect more subtle by basically weighting it with our old-fashioned linear. By weighting the t prime with the original t. Some balance, and you can choose how much. You can have, like, almost imagine having a slider, all linear, all this nonlinear system. So for example, you could imagine t double prime is going to be a times t prime plus 1 minus a t, where a is your mixing factor. Okay, so you can balance between the two using the same old linear combination business we've been using for a while now. So let's look at the notes, demo rather. So what I've done here for level is I just took the ease in and out that I had above, and I divided it by 2. I could just divide by 4, but I did this to show you that I'm dividing this by 2 and adding half of 2. So I'm averaging them both. You know what? It's probably cleaner just to do it this way. T plus t prime over 2, right? So I'm going to calculate that, and what you'll get is you'll get the same effect as the ease in and out, but it'll be less dramatic. It'll be a little more subdued, and I want to show you this. Ease in, ease out. Okay, ease in and out. And it looks a little lively, a little subdued, a little active. And if I put the level in, it's just a little more subtle. It's still there, but it's a little less bouncy, let's say. It's a little less accelerating, decelerating. The top speed is lower, so it's a bit more balanced. So this is called leveled, easing in and easing out, and you can kind of balance those two with the slider. So we're just scratching the surface here of what we can do with interpolation. I'm just showing you the basics. You can imagine that you can come up with all kinds of really funky functions to do things. You can add noise in there so it jitters along the way. You can add minuses so it goes backwards sometimes, and like you can imagine all kinds of really cool things. But for now, I'm just showing you the basics of how you take a linear function like lerping, which is really cool, but then you want to make it non-linear, and you can do that in all sorts of ways, and probably the most common way you'll come across is just using patches from sinusoids to calculate a t prime that's non-linear, that makes t change in a non-linear fashion. So that's really cool. All right,